All right, let's take a look at our next example. We've got limit as x approaches infinity of the natural log of x divided by x. Step 1, direct substitution. So what is the natural log of some super large number getting close to infinity? Well, one way to think of it is look at the graph right here. Here's the natural log x. As x gets bigger and bigger and bigger, natural log is 2. It's just really super slow. So it's still going to infinity. And then on the bottom, of course, this is just x down here at the bottom. It should also go to infinity. Got infinity over infinity, which is a check for L'Hopital's rule. All right, let me just kind of be a little bit more clear here, and that is when I have to do this on the free response section, this is the kind of thing that the readers are actually looking for, and it looks like this. I would separately take the limit of the top and the bottom like this. The limit as x approaches infinity of the natural log of x, that is equal to infinity. It does not exist due to unbounded behavior, and you can do that. Like I'm thinking of the graph on this thing that it's going to infinity. That's right there, right? Okay, and then I take the limit as x approaches infinity of just x, and that's also equal to infinity. And so here I avoided like this equal sign that would have been, that's right here, that I usually use this little arrow here. And now you can say, by L'Hopital's rule, yeah, there we go. What's this actual, oh, it's this thing, that's what that wants to be. You take the limit as x approaches infinity of the natural log of x over x, and we take the derivatives of the top and the bottom. The limit as x approaches infinity of derivative of the natural log of x, just 1 over x. Derivative of x is 1. So just out of convenience, I'll rewrite this as the limit as x approaches infinity of just 1 over x. That'd be 1 over infinity, 1 over infinity. That's a 0. Okay, so we have the limit here is equal to 0. It's getting closer and closer to 0. You know, there's probably another way to think about this, and it's right here in this picture that's right here. Let's look at a better picture of this. Let's look at the graphs of both of these two functions. Here's the natural log of x, and here's y equals x. Isn't this y equals x growing way faster than this natural log of x? Remember that whenever we were talking about the pre-cal rule for taking limits at infinity for horizontal asymptotes, what we can do is just look at the ratio of the coefficients or something like that. And it's based on the fact we're talking about relative growth rates. The top is growing, that's the natural log, is growing way slower than the bottom is. So we have a really small number divided by a really big number. This should be approaching 0. And that kind of explanation or that kind of justification is perfectly acceptable on the AP exam. It's about relative growth rates. Relatively, y equals the natural log of x growing much slower than y equals x, so the limit is approaching 0. Now, once again, let me go and actually I'm going to go to the web here and let's take a look at, this is the scoring guidelines, not what I want to look at. Here was a free response question 2018. This is on the AB exam. May have been also on the BC exam. Okay, it's question number 5, which means it's without a calculator. You're given this function, f of x is equal to e to the x times the cosine of x, and you had to do some things that we can do. We can do 100% of this thing now. You're finding the average rate of change, as you can see. We are finding average rate of change is not calculus at all. Remember, that's just the slope of the secant line. Part B, what's the slope of the tangent line at a particular point? What's the absolute minimum value on the interval? Remember that you have to use the closed interval test for that, and they give you a closed interval. And then finally, part here on D, let G be a differentiable function such that G of pi over 2 is equal to 0. The graph of the derivative of g is shown below, and it gives us a picture of the graph of the derivative instead of like a function for it, right? Okay, we want to find the limit, the value of the limit as x approaches pi over 2 f of x divided by g of x, or state that it does not exist. Oh, and look at this, justify your answer. So justifying your answer, I want to be as thorough as possible as like how I'm supposed to approach this, and after I get my answer, why is that answer actually valid? Chances are, if there's a limit on the response section, you're having to use the L'Hopital's rule, so you have to justify that you can use L'Hopital's rule. You can only use it if you have the indeterminate form 0 over 0 or infinity over infinity. Let's look at the scoring guideline for this. It's just part D that's right here that I'm concerned about. And notice that it says that the limit as x approaches pi over 2 of f of x is equal to 0, which I do believe is what we needed for, my gosh, I don't remember what that, it was f of x on the top. So right there, they said that the limit of the top was equal to 0. Okay. And then on the bottom here, because g is differentiable, it's continuous, and then they take the limit of the bottom. If your function's continuous, remember that the value of the limit and the function value is exactly the same. That's how I know that I can do it. Okay, so over here in the scoring guideline, notice that it wants us to say that g is continuous at that particular point in order to evaluate that limit. That was worth a point. Okay, so now they have the tops equal to 0, they have the bottoms equal to 0. Now that they can apply L'Hopital's rule by taking the derivative of the top and the bottom and then evaluating each one of those functions at the derivative. How did they get the derivative of 2 for the bottom function? Well, they have a graph, and so we have the graph of the derivative. All we're finding here at pi over 2, you can see that it hits at 2.